Hi everyone, welcome to the section on autoencoders. So autoencoders are a special kind of deep learning models which can be used both in supervised and unsupervised fashions. They have many applications in different areas and they can be used in different ways with the dataset. Let's see what we are going to learn in this section. So first we will learn about the architecture of the autoencoder. We will see it is a special kind of deep learning which has two important components, that is encoder and decoder. After study the architecture, we will discuss in detail about the applications of autoencoder. The most important applications are that we can remove noise from the data, especially from the images with the help of autoencoders. We can remove occlusion from the data with the help of autoencoders, and we can also use autoencoder as an image classifier. So when we use autoencoder for removing noise or to remove occlusion from the data, in that case, autoencoder will be used in an unsupervised fashion. That is, we only need the data, we do not need label when we have to remove the noise or we have to remove the occlusion from the data. But when we use autoencoder as an image classifier, in that case, we will use it in a supervised fashion. Therefore, it is a special kind of deep learning model which can be used both in supervised application and in unsupervised application. After that, we will implement all these three applications in PyTorch with the help of three projects. So I hope you will learn a lot in this section about the autoencoders. Thanks for listening, and I will see you in the section. Hi everyone, welcome to this lecture. So in this lecture, we are going to learn about the architecture of the autoencoder, and we will also learn how autoencoder works. So basically, auto means self and encoder means transform information to another form. Therefore, autoencoder is a deep learning model that learns how to encode information. So what happens in autoencoder? When we apply input to the autoencoder, then with the help of the encoder, which is the important component of the autoencoder architecture, the encoder extract the information from the input data. That is, it encode the information to another form. Then later on, there is another important component in the architecture of the autoencoder, which is the decoder. Decoder is used to decode the information back to the original form. So this is the working of the autoencoder. This is the typical architecture of the autoencoder. We can see that it has 5 different kinds of layer. It has input layer, encoder layer, then latent layer, decoder layer, and finally the output layer. If we see the dimensions of each layer, the dimension of input is k and the dimension of output is also k. Then the dimension of the encoder layer is n and the dimension of decoder layer is also n, whereas the dimension of the latent layer is n. So if we see here, k is greater than n and n is greater than m. It means input and output layers are of higher size in the architecture of the autoencoder, and then is the size of encoder and decoder. The latent layer is of very small dimension as compared to encoder, decoder, input and output layer. So what we are expecting from the autoencoder, that if we supply input of k dimension, then autoencoder should be capable of giving the output whose size is same as that of input. So basically what happens in autoencoder, when we apply input to the autoencoder, then first comes the working of the encoder layer. Encoder layer encode the information from k dimension to n dimension. Initially, the dimension of the input data is k. So with the help of encoder, we not only encode the information, we not only extract the features from the input data, but we also reduce the dimension of the data from k to n. Then with the help of latent layer, we further extract the information and we further reduce the dimension of the data from n to m. In that way, up to latent layer, the dimension of the data reduce from k to m. So in this way, we can say that autoencoder can be used to suppress the data, to compress the data, or to reduce the dimension of the feature space. Here at input, the dimension is k, and at the latent, the dimension is m. So we have not only encode the information, we have not only extracted the information, but we have reduced the feature dimension of the data as well. So what is the advantage of that feature dimension or reducing that feature dimension? So basically, what happens when we reduce high dimensional data to low dimensional data with the help of the autoencoder? In that case, there are many unwanted things which are removed. If there is noise at the input side of the data, that noise will not be present when it reach to the latent layer. Similarly, there are many other unwanted things which we want to clean from the data. Then when we reduce the dimension of the data or reduce the dimension of the feature with the help of the autoencoder, that unwanted things remove from the data. And later on, we decode the data, and then with the help of the decoder and with the help of the output layer, we are able to recover the data back into the original size. So we can see that if the size of the data at the input layer is k, at the output layer, the size of data is also k. But in between, we reduce the size of the data, we reduce the size of the features which are extracted from the data from k to m. By reducing the feature, we are able to clean the data, we are able to suppress the data, and we are able to remove unwanted things from the data. So this is the working of the autoencoder. First, it is going to encode the information and reduce the dimension from k to m, and then we use the decoder and we increase the dimension back to k from m. So in this way, we expect autoencoder to generate the output which should be exactly as that of input, not with respect to size, but with respect to features as well. But in between, we are able to reduce the dimension of the data with the help of the latent layer. This is another representation of the autoencoder architecture. In the previous figure, we represent the layer with the help of nodes. Here we are representing just with the help of layers. We have an input layer, encoder layer, decoder layer, output layer, and this is latent layer. Latent layer is also known as bottleneck layer. Here again, we can see that the dimension of input and output are same. Similarly, the size or the dimension of encoder and decoder is same, and it has the lowest dimension, which is the latent layer. Now, student, we can see that we have one layer in the encoder and one layer in the decoder. So this is not necessary. There could be many layers in the encoder side, and there could be many layers in the decoder side, depend upon the size of the data and depend upon the task which you are going to perform with the help of autoencoder architecture. So this is the another autoencoder architecture. Here we can see that we have more than one layers in encoder, and also we have more than one layers in the decoder. So it is possible that you can add many layers in the encoder component of the autoencoder and also in the decoder component. It depends upon the task. It depends upon the size of data. So this is the working of autoencoder. We can see that we are inputting an image to the input layer of the autoencoder, and we are expecting autoencoder to produce the same image at the output. So between this input and output layer, there is encoder, there is a latent layer, and there is a decoder layer which works on the input, which extract feature from the input and which reduce the dimensionality of the input. By reducing the dimensionality of the input, we are also able to clean the data. We are also able to remove the noise, and we are also able to extract useful features from the input data. So this is the working of the autoencoder, that we expect from the autoencoder to generate the output which is exactly the same as that of input. So student, in this lecture, we learn about the architecture of the autoencoder. We learn that it has 5 different kinds of important layers, that is input layer, encoder layer, latent layer, decoder layer, and the output layer. And in encoder and decoder, there may be more than one layer, depend upon the task which we are going to perform with the autoencoder. So I hope you understood the fundamental architecture of the autoencoder. I hope you understood how autoencoder works on the input data and how it reduces the dimensionality of the input data. Thanks for listening this lecture, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to discuss the important applications of autoencoder. So the first important application is reducing feature dimension. The second is removing noise from the data. The third is removing occlusion from the data. And the fourth application is that autoencoder can be used as an image classifier. So in the previous lecture, we have learned about the architecture and the working of autoencoder. We saw there that if we apply input to the autoencoder not only extract the information from the input data, but it also reduce the dimension of the input feature. Therefore, autoencoder can be used easily in order to reduce the dimension of the feature by using the encoder layer and the latent layer. The second application is that we can remove noise from the data. So what happens if we supply the noisy image at the input of the autoencoder? Then when we reduce the dimension of the input image from input layer dimension to the latent layer, in that case, we are able to suppress the data. During the suppression of a data, the noise is also removed from the data. So in that case, with the help of the encoder layer and the latent layer, we are able to remove the noise from the data. The third application is removing occlusion from the data. And the fourth application is we can use it as an image classifier. So like convolutional neural network and like artificial neural network, we can also use autoencoder in order to perform the image classification. So the first application is the autoencoder is a noise remover. This is my input data, and due to some reason, a noise has been imposed on that input data. Now I want my autoencoder to remove this noise so that I can get my original images back in the original form. So what happened when I pass these noisy image to the autoencoder suppress those images with the help of encoder layer and latent layer. During this suppression, autoencoder is able to remove the noise from the input images. Later on, with the help of the decoder, we are able to extract the sizes or the original shape back to the original form, which is displayed at the output layer of the autoencoder. So in this way, autoencoder is used to remove the noise from the input data. If we see here, this is the image after the noise removal. It is not exactly the same image as that of the input image, but it is still readable, it is recognizable, and we can still recognize that this is a digit 9. Similarly, if we see this 5 and this 5 after the noise removal is not as sharp as that of the input image, but this is still recognizable and we are able to read this image as a 5. Similarly, all the input images and all the output images are recognizable. The output images are not 100% equal to the input images, but they are very close to the input image and they are recognizable. The second application is the occlusion removal. So what is occlusion? Occlusion means if I have an important object in the image which is hidden by some another object, then it is called the occlusion. Here I can see that this might be the image of a bird, but it is hidden behind some grids. In that case, I am unable to locate the important object and I am unable to recognize this important object. So I need to remove the occlusion so that I can identify my image. So autoencoder is also the occlusion remover. These are my original image and we can see that here we have the occlusion on these images. This is the occlusion in the horizontal direction, that this is the horizontal occlusion. So what will happen? We will pass these occluded image to the autoencoder and autoencoder will suppress the size of the image, and during suppression it will remove the or it will try to remove the occlusion from the image, and after that with the help of decoder we will be able to generate those image back to its original size. So if we see here, this is 1. Here is the occlusion. After occlusion, we can see that we are able to remove almost 80% of the inclusion effect and we get the output image which is recognizable. We get some occlusion here which we are unable to remove with the help of autoencoder. Similarly, we can see that from the 0, we are able to remove around 80% occlusion but there is still some occlusion present at the output. Similarly, if we see this 2 is not very much recognizable after the removal of the occlusion. It can also be recognized as a 3. So what happened that when we pass the occluded data to the autoencoder, then autoencoder has the ability to remove the occlusion from the input images. This is the loss function of the autoencoder. If we see, this is mean square error loss. So basically, if we see, this is my input image and this is my output image. The output image is not exactly same as that of the input image. Therefore, we have an error. So this is input, this is output. So if I subtract them, I will get the error. And here I am squaring the error and I am taking the mean of the error. So the loss function of autoencoder is mean square error when it is used for the noise removal or when it is used for the occlusion removal. Here is another application of the autoencoder, that autoencoder is also an image classifier. When we use autoencoder as an image classifier, we only use the encoder layers. We do not use the decoder layer. So in that case, we supply input data to the encoder layer, and encoder layer are working as the feature extractor. They extract all the important features from the input data and then pass these features to the classification layer, which perform the classification. So the important concept is, when you want to use autoencoder as an image classifier, you have to remove the decoder part, and at the place of the decoder part, you have to attach a classification layer so that you can perform the classification. So these are the few applications of the autoencoder. I hope you understood these concepts. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to solve our project 1 on autoencoder. So here I am in my Google Drive. This is my course material folder. Click on this folder. Inside this folder, I have supervised machine learning folder. Click on this folder. Inside this folder, I have folder known as autoencoders. Click on this folder. Inside this folder, I have my project 1 autoencoder denoiser. So basically in this project, there are 2 objects. So the first objective of this project is that we are going to learn how to implement autoencoder in PyTorch. And then we will learn how to use autoencoder to remove the noise from the images. Let's click on this file so that we can open it in our Google Colab environment. So this is my project 1. For project 1, I need these libraries. Let's run this cell to import these important Python libraries. Now in this project, I am going to use MNIST train dataset, and that dataset is present inside my folder. And we know that in order to read the dataset from the folder, we need to mount the drive, we need to set the path. So in order to save the time, we have already mounted the drive and we have already set the path. Okay, now it's time to read the data. Let's run this cell to read the data. So after mounting the drive and after setting the path, we have successfully read the data. Now it's time to transform the data to the NumPy array. And in the next step, we are extracting first 10,000 samples from the data. Let's run this cell. So we can see that we have successfully extracted first 10,000 data samples from the MNIST data. Now, in this project, we are going to use the autoencoder in order to remove the noise from the image. Therefore, we do not need labels. We only extract the features from the data. That is, we extract the data without labels. So here we are extracting the features from the data and we are calling it data. Here we are normalizing the data. And here we are converting the data into PyTorch tensor. Let's run this cell to perform all these steps. So this is the architecture of the encoder which we are going to implement in this project. So the size of the input layer is 784 and the size of output layer is also 784. We know that in autoencoder, we expect autoencoder to produce the output whose size should be the same as that of the input size. The size of the autoencoder layer is 256 and the size of the decoder layer is also 256. The size of the latent layer which we are going to use in this project is 64. So we are going to implement this autoencoder in this project with the help of PyTorch. So I am using a class in order to create the autoencoder. So this is the class of the autoencoder. This is starting with the keyword class. Then I have autoencoder model. This is the standard stuff which is necessary in order to create the class. So here are my layers: input layer, encoder layer, latent layer, and the decoder layer. So we can see that at input layer, the first feature is 784, because we are going to use the MNIST data here, and we know that the size of MNIST images are 28 by 28, and if we multiply them, we get 784. Therefore, the input feature to this input layer is 784, and then we are using 256 as the output feature. So 256 is basically the size of the encoder layer. If we see this, the 256 is the size of the encoder layer, then the latent layer, and then the decoder layer. If we see, we start from 784 and we end up at the 784. So the size of input layer is equal to the size of the output layer. 256 is the size of encoder layer, and 256 is also the size of the decoder layer. Okay, now it's time to define the forward path or the forward function for this class. So this is my data. I am passing this data first to the input layer. Then I have an activation function, which is a ReLU. Then I pass my data to the encoder layer. And then I am again using ReLU as an activation. Then I am passing my data to the latent layer. And finally, I am passing my data to the decoder layer. After decoder layer, I am using a sigmoid function. And here is the reason why we are using the sigmoid activation function, because we have normalized the data between the range of 0 and 1. And we know that the limit of sigmoid is also between 0 and 1. That is, the minimum value of sigmoid function is 0 and the maximum value is 1. Here I am returning y from this function. Let's run this cell to create the class. Here I am creating the model instance, and I am setting the parameters. So model is AE underscore model. So this is the name of the class, and I am here creating the instance of the class, and I am calling it as a model. So the loss function I am using is MSC loss. We know that we are not going to perform any classification in this particular project. Therefore, the loss function is not cross entropy loss, but it is MSC loss. We use MSC loss because we want to remove the noise, and after removing the noise, we want that our output should match the input. Therefore, we are going to use MSC loss function. The optimizer which we are going to use here is the Adam optimizer, and learning rate is 0.001. Okay, let's run this cell to create the model instance. Now it's time to train the model. So I am going to train the model for 10,001 epochs. Here I have initialized the losses so that I can calculate the loss for each of the epoch. And here I am running a for loop for the epoch. Now, student, the important thing is, here I am training my model in the batches, in the form of batches, and the batch size is 32. But I did not use train loader or a test loader. The reason is that we do not have label in this project. Therefore, we can train the model without the using the data loader. But we have to set the batch size here. So this is another method which we can use in order to set the batch size of 32 without the data loader. So let's see what this line of code is doing here. So basically, we can understand here what this line of code is doing. If we see here, this line of code will generate 32 random indices. This is the size. So it will generate 32 random indices, and the value of indices is between 0 and 10,000. The data t.shape, this data t.shape 0 is 10,000 because we have 10,000 sample in our data. Let's run this cell to understand the working of this particular code. So we can see that we have 32 random indices. These are 32 random indices whose values are between 0 and 10,000. If I run this cell again, I will again get the 32 random indices, but of different indices. Now you can see that this value is 40. Here the minimum value is 40. So the values are between 0 and 10,000. We can see that we have a very high value here. If I run this cell again, I can see that the values are between 0 and 10,000. So what will happen? I will use these indices. I will use, or I will pass these indices to my data, and I will get the 32 images. So every time this epoch will run, after that, this line of code will be executed. And each time this line of code will generate different 32 indices. Therefore, we will use those indices to extract different 32 images from the data. Here I am passing X from my model, and here I am getting the prediction. If you see in the loss function, this is another very important step. Here I am comparing the prediction of the model with the original input because I do not have label in the project. I want the prediction of the model to match the input. This is the backpropagation, and here I am accumulating the loss, and here I am printing the loss for the epochs. Okay, let's run this cell to start the training. So we can see that after 1000 epoch, our loss has reduced to 0.02. So we have decided to train the model for 10,000 epochs. Now, student, important thing to remember about this training is that we are training the autoencoder on the input data which doesn't have noise. We have not introduced any noise yet in the project. So what will happen? First, we will train the autoencoder on the data which doesn't have any noise. After that, we will pass the noisy data to this trained encoder, and we will expect that this trained encoder will be able to remove the noise. So during the training, we will not pass any noise to the autoencoder. We train the autoencoder on the original data, which is not a noisy data. But when the autoencoder is fully trained, then we will pass the noisy data, and we will expect autoencoder to remove that noise. So these are the steps of this project. So here you can see that we are training our autoencoder for 10,001 epochs, and here the data which we have passed to the autoencoder for training doesn't have any kind of noise. Okay, let's see the performance of the autoencoder. So we have reached up to 9,000 epochs here, and loss has reduced to 0. So here the training is completed, and we can see that the loss has been reduced to 0. Okay, let's visualize the performance of the autoencoder. So we can see that the autoencoder has performed very well. At the start, the loss was a bit high. Then as the epochs passes, the loss has reduced and finally reached to the 0 value. So the autoencoder has now fully trained on the input data. Now it's time to test the model. So we are extracting first 7 samples from the data. And after extracting the first 7 sample, we are passing it to the model to get the predictions. Let's run this cell. Now model has produced the prediction. Let's visualize the prediction and compare it with the original data. So here I am creating subplots which has 2 rows and 7 columns in each rows. And here I am running a for loop with the range of 7. Here I am plotting the original images, and here I am plotting the predicted data, and I'm transforming it to 28 by 28 size. Let's run this cell to visualize the test performance. So we can see that these 7 are our original images, and these are the images predicted by the model. We can see that model has done a great job, and it is able to replicate our input images at the output. We can see that this 5, this 0, this 4, they are all recognizable digits. Now we have trained the model, we have tested the model, we have trained the model on original data without a noisy data, and we have also tested the model without the noise. And now we are satisfied with the performance of the model, that it has the ability to replicate the input at its output. Now we are creating a noisy images so that we can pass those noisy images to the autoencoder, whose function would be to remove the noise. Here I am again picking the first 7 images. Here I am adding Gaussian noise to the images. So these are my images, and here I am creating the noise. So the size of the noise should be equal to the size of the images, because we are going to perform the addition. For addition, the size should be the same. So here I have created the noise. Here I am adding the noise to the original images, and I am calling it X noise. Now, this is another very important step. What has happened? We have normalized the data between 0 and 1. So there are many pixels in the data whose intensity is 1. When we add noise on that image, so there will be many pixels whose value will try to increase from 1, that is, it may become 1.1, 1.7, 1.8. So we are clipping the value which is higher than 1 back to the 1, so that we can retain the original information in the image. So basically, when we add the noise, by adding the noise, few pixel will try to get the value more than 1. In that case, we will clip the value which is more than 1 here. So we are ensuring that our data will remain normalized between 0 and 1. Okay, so here is the noise, and here I am plotting again my original images, and here I am plotting the noisy images. Let's run this cell. We can see that these are our original images, and we have created the noisy images. We can see that we have created a large amount of noise on top of the images. So this is 5041921, and this is the noisy image. Now, what is our expectation from the autoencoder? Our expectation is that when we pass these noisy images to the autoencoder, it will be able to produce these kind of images. Okay, let's perform the denoising. Let's remove the noise from the images by passing the noisy images through the model. And here we are getting the prediction from the model. Let's run this cell to get the prediction. And here I am plotting the original image, the noisy image, and the prediction. And I am expecting that the predictions of the model should be exactly equal to my input images. Let's run this cell. So we can see that we have 3 rows of the images. We have 7 images in each of the row. These 7 images are my original images. These 7 images are the noisy images. And these 7 images are after the removal of the noise. Now we can see that our model has done a great job. If you see this 4 is not exactly same as that of the input, but it is still recognizable. Similarly, if we see this one is not as sharp as that of the input image, but it is still recognizable. So we can see that when we pass the noisy images to the autoencoder, it has the capacity, it has the ability to produce the output which is noiseless. So in this project, we learn how to design autoencoder, how to create autoencoder with the help of PyTorch. Then we train autoencoder on the original images where there was no noise. And when we satisfied with the performance of the autoencoder, then we create the noisy images, and then we pass the noisy images to the autoencoder so that autoencoder could remove the noise. We observe that autoencoder has done a great job in order to remove the noise from the input images. So I hope, students, you have enjoyed this lecture. I hope you understood the concept of creating the autoencoder, and you understood how autoencoder could be used to remove the noise from the images. Thanks for listening this lecture, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to solve our project 2 on autoencoder. In this project, we are going to remove the occlusion from the images. So basically, in this project, we are going to use the same dataset, that is the MNES dataset, which we used in the project 1. Furthermore, we are going to use the same architecture of the autoencoder, which we designed in our project 1. Let's run this cell to open this file in our Google Colab environment. So student, here I am in my project 2, in which I am going to remove the occlusion from the input images. Now student, at the start of the project, the 80% code is exactly the same code which we saw in the previous project. Therefore, I am not going to go through it in detail. In the first cell, we have imported the Python libraries, then we mounted the drive, we set the path, we read the data, we create the autoencoder. If you see the architecture of the autoencoder, it is exactly the same architecture which we used in our project 1, that is the previous project. Here I am creating the instance of the model. I am also setting the loss function and the optimizer. And here I am training the model for 10,001 epochs. So this is the training. This is the same training which we saw in the previous project as well. Here we have visualized the performance, and we saw that model has done a great job. It has reduced the loss to 0 when it has reached to 10,000 epochs. Then here is the new thing. Here we have to explain how we have occluded the image and how we remove the occlusion. So first I am extracting, or I am copying first 7 images from the original data, and I am calling it X. Here I am running my for loop for 7 times because X dot shape 0 is 7. So I am running my loop 7 times. Here I am transforming my data to the image of size 28 by 28. Here I am extracting a single value. I am using np.random.choice. The range is 5 into 20. So basically, every time this line of code will run, it will generate a value between 5 and 20. The reason is that the size of our image is 28 by 28. So we have to occlude the image. Here I am getting a value, and I will use that value to occlude the image. Suppose during the first run of the for loop, a value which is coming out from this line of code is 6. So I will put 6 here as the index to this image. So this will be 6, and this will be 6 is to 7. And I am going to use all the columns. So I am going to occlude the image row wise in this project. So it will be 6 is to 7. 6 is to 7 means out of the 28 images, I am going to occlude the 6th row of my image. When this for loop will run for the next time, this line of code will generate a different value between 5 and 20, and we will use that value in order to occlude the row of our image. So these lines of code are used in order to occlude the image. Here I am performing de-occlusion. I am passing occluded data to my model, and I am getting the prediction from the model. Here I am plotting 3 values. If you see, this is the original data without the occlusion. This is the data with occlusion. We can see the row-wise occlusion. We have occluded the data row-wise. And this is the de-occluded data. This data is the prediction of the model which has performed de-occlusion. If we see the model performance, it is more than satisfactory. It is a good performance. We can see that for the first image, the occlusion is almost removed. If we see here, there is a slight occlusion here. If we see 4, there is a slight effect of occlusion here at the output or at the predicted value of the model. If we see 1, we can see the effect of the occlusion as well in the 1. If we see 9, this 9 is also not very sharp as compared to the original 9. If we see this sample, this is the most affected sample. We are not able to recognize it properly. We can recognize it as a 3, and it is actually 2. So we can see that here model is not performed well for this particular image. Here again, we can see the effect of occlusion. So we can see that model has done a great job, and we are able to recognize most of the digits after the occlusion. So in this project, we learn that autoencoder can be used to remove the occlusion from the image. We observe that autoencoder has the capacity to remove the occlusion from the image, and it has the capacity to duplicate the original images after the removal of the occlusion. So I hope you understood this project. In this project, about 80% of the steps were same as that of the project 1. So I explained you only the occlusion part of this project. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to solve our project 3 on autoencoder. So basically in this project, we will learn how we can use autoencoder for the classification problem, and how we can use autoencoder basically for the image classification. Okay, here I am inside my autoencoder folder, and this is my project 3. Click on this so that we can open it in our Google Colab environment. So here I am in my project 3. In this project, I am going to use MNIST data again. Therefore, in order to save the time for this project, I have already mounted the drive, and I have already set the path, and I have already read the data here. Okay, now in this line of code, what I am going to do is I am going to transform the data into NumPy array and here I am extracting first 1000 sample from the data. Okay, let's run this cell, and we can see that now we have first 10,000 samples of our data, which we will use for the experimentation. Now, student, in this project, we will do two things. There are two steps in this project. First, we train a complete autoencoder. That is, we train both the encoder and decoder part of the autoencoder. We train a complete autoencoder without the labels, which is the unsupervised learning. And when we see that our autoencoder is performing well, and when we satisfy with the performance of autoencoder, then we will do for the classification. For classification, we will remove the latent layer and the decoder layer from the autoencoder, and we connect the classification layer in order to perform the classification. That will be supervised learning. So in the first step of this project, we will perform unsupervised learning, where we do not need labels, and we train full autoencoder in order to check the performance of autoencoder on our dataset. And in the second step, we remove the latent layer and decoder layer and connect the encoder with the classification layer in order to perform the classification. And that part of the project will be the supervised learning. Okay, since I do not need labels, therefore I am extracting only the features from the dataset. Here I am performing data normalization, and here I am converting NumPy into torch.tensor. Okay, let's run this cell to perform these three important steps. Now, student, this is the architecture of the encoder which I am going to implement in this project. Okay, if we see, the shape of input and output is 784. The shape of encoder and decoder is 256. And there are two layers basically in encoder and decoder. The second encoder layer is 128, and the decoder first layer is also 128, and we have the latent layer in between, which has the dimension 64. So in this particular project, we are going to use the autoencoder, which has two layers in the encoder and two layers in the decoder. Now we have to implement this autoencoder for the MNIST dataset, and we will have to see the performance of this autoencoder. When we will be satisfied with the performance of autoencoder, then we will remove that part of the autoencoder, and we will connect the encoder with the classification layer in order to perform the classification. So that will come later in this project. Okay, so the first step is to create this autoencoder using a PyTorch. So here I am creating autoencoder. So I am starting with the keyword class, and the name of the class is AE_model. Here I am defining the input layer. So input layer size is 784. So this is 784, and the output feature of the input is 256. Then I have encoder layer. So in encoder, I have two layers. So the first layer starts from 256 and its output features are 128. Then the second encoder layer starts from 128 and its output features are 64. Then the latent layer starts from 68 and its output features are 128. Similarly, these are the two decoder layer. The first decoder layer starts from 128 features and it ends with 256 features. The second decoder layer starts from 256 and it ends with 784 feature, which is the size of the MNIST image. So the input layer is 784 in dimension, and output layer dimension is also 784 here. So here we have defined the layers. Here we have the forward function. First, I will pass my data from the input layer, and then I am going to pass it to the activation layer, which is the ReLU this time. And again, I am passing my data to the first encoder layer and then the activation. Then I am passing my data to the second encoder layer, then the activation, and then I am passing my data to the latent layer and then the activation. Similarly, I am passing my data finally towards the decoder, through the decoder, and first from the first decoder layer, then the activation, then the second decoder layer, and then we are using sigmoid as a activation function, and here we are returning X. Okay, so this is our autoencoder. This is the autoencoder which we are going to use here. Let's run this cell to create the autoencoder class. Okay, here I am creating the model instance and setting the parameters. So model is AE_model, and loss function I am going to use is nn.msc loss. since I am going to train autoencoder without labels, that is for unsupervised learning. Therefore, I am going to use MSC loss function, and I am expecting my autoencoder to duplicate the input exactly at the output. Okay, let's run this cell. And now here we are training the model for 15,001 epoch. So this code is exactly the same as that of the code which we saw in the previous two projects on the autoencoder. So when we train the autoencoder, we see that after 50,000 epoch, our loss has reduced to 0.01. At the start, it was 0.23. Then slowly and slowly it reduces to 0.01. This is the performance visualization of the autoencoder, and we can see that it has performed well. Its loss has been reduced to a very low value after around 15,000 epochs. Now for model testing, what we have done is we have extracted first 7 sample. Here we are passing those samples to our model to get the prediction. And here we are visualizing the test performance. Now we can see that the model has done a great job. This model has doing a great job. These are the input images and these are the predicted images of the model. We can see that almost all the digits are recognizable. We are not observing any noise at the output of the autoencoder. It means this autoencoder is performing a great job. It encoder has an ability to extract the feature from input. Now we use the same architecture of the autoencoder for the classification problem. Let's start the classification problem. Now for the classification, if you see, we are using the input layer, we are using the encoder part, and then we connect our encoder with the classification layer. So after encoder, we have removed the decoder and we connect the encoder with the classification layer. So this is the architecture which we are going to implement as an image classifier. Here I am define or I am creating the autoencoder for the classification using a class. So I'm starting with the keyword class, and then I am calling it AE underscore classifier, that is autoencoder classifier. Here I am defining the input layer. These are the two encoder layer, and here is the change. I am connecting the second encoder layer with the output layer. So this 64 will be connected with this 64. And since in MNIST data, we know that we have 10 digits from 0 to 9. So we have 10 classes. So this 10 represent the number of classes. And here is my forward function. I am passing my data to the input layer, then from the first encoder layer, from the second encoder layer, and then from the output layer. Okay, let's run this cell. Then create the model instance. Now I am going to read the data for the classification purpose again. The reason is that this time we need both features and label because we are going to perform a classification which is a supervised learning. So I am reading the data again. Here I am transforming the data into NumPy array and extracting 10,000 sample. That is the first 10,000 sample. And here I am extracting features and labels from the MNIST data. Now these are the 4 important steps. We can see that here I am transforming NumPy array into torch.tensor. That is, I am transforming my features and labels. Here I am going to perform a train test split. I am going to set a test size of 10%. Here I am normalizing the training and the testing component. Here I am transforming the train labels, test labels, train data and test data into PyTorch dataset. And here I am pushing the PyTorch dataset or tensor dataset into data loader. I am using a batch size of 32 for the training component, and I am not using any batch size, but I will pass whole the test component at once during the testing. So this is again very standard stuff. We have done this before in the previous sections of the course. Let's run this cell to perform these 4 steps. Now for classification, I will use GPU. Let's print the device. So device is CUDA. GPU is available. Let's start training. So I am going to train it for 101 epochs. Here is the difference. Now I am not going to use any MSC loss. I am using cross entropy loss because I am going to perform a classification problem. Here I am putting my model to device, and rest everything is same, which we have seen many times in the training and testing code of the deep learning model. So let's run this cell for 101 epochs, and we will see the performance. Here I am printing the loss versus epochs after every 10 epoch. So the training has started. Training and testing has started. Here we have put the model into the testing state, that is put model.eval. Here I am passing the whole test data to the device, and during testing, we do not require any gradient. So these are the same steps which we have seen many times when we design the classifier. So training has been started. We want to train the model for 101 epochs. So here first 51 epochs has been completed. We can see that at the start of the training, the loss was 0.49. After 10 epochs, it reduced to 0.01, and after 20, it has been further reduced to 0. So we can see that the loss is still 0. If it remains 0 after 101 epochs, then we will expect 100% accuracy on the training. So the training has been completed. Let's visualize the classification problem. Let's run this cell. So we can see that in a training loss, the loss starts from some high value, but as the epoch passes, it has reduced to 0 after 101 epochs. Look at the performance of autoencoder as a classifier. So we can see that the performance of autoencoder as a classifier is also very good. Train accuracy is 100%, and the test accuracy on MNIST data is also very high, which is 96%. So in this lecture, we learn how to use autoencoder as a classifier. We see that first we need to design a complete autoencoder and train autoencoder in an unsupervised learning fashion and see the performance of autoencoder. When we satisfy with the performance of the autoencoder, especially with the performance of encoder, that it has extracted all the important feature from the input, then we remove the second part of the autoencoder and connect the input and encoder layer with the output layer in order to perform the classification as shown here. So in this lecture, we learn how to design an image classifier based on autoencoder. So I hope you understood this lecture very well. Thanks for listening, and I will see you in the next lecture.